Yes, I have it here. Which one is yours? Yours is this one, right?
Yep.
I think you only have. I think you missed a lot.
Me? How many is that?
1, 2, 3, 4. That's the last 2 classes. You missed 2 classes.
So 3, does it already equal to fail? Or if one more is fail?
To be honest, I don't know. How many classes do we have?
Okay, I'll talk to the professor.
Yes.
Thank you.
Okay, let's start. So we have a test next week, and the test goes up to the homework that is due before the test, which means homework which is due on the 18th. Oh, sorry. Let me. Yeah. The test will include even that homework that is due on the 18th. Okay, even though the 18th is after the test. Okay? So please note that. So there's this homework here. Here, this one is due on the 18th. Okay, but it will be included in the test. Okay, everyone follow that? Okay, so today, let's go through all the rules for derivatives so that we can then forget about all the sort of abstract or mathematical stuff. We'll just say, oh, we know it now. Then we can use it for different applications. Okay, so I'm going to get these rules. So there's, I guess I forgot another one here. Let me put another one that should be after number 1, but I'll just call it number 4. Number 4 should be after number 1. It says that the derivative of k times f of x equals k times the derivative of x. An example, it's like derivative of 10 times x cubed is 10 times the derivative of x cubed. Okay, so anyway, let's read this. So these are rules for doing derivatives. And all of these rules can be proved by going back to the original definition of the derivative. And we can prove these, but we're not going to do that, but you can look them up. So the first one, and I said I'm switching, just because it's easier sometimes to use one notation versus another. Sometimes I'll write the derivative like this, and sometimes I'll write it like that. Okay, just switching back and forth when I express it. So this first one says the derivative of f plus g, or also there's another rule for minus g, but let's just concentrate on plus, is the derivative of f plus the derivative of g. So example of that would be if you wanted to know the derivative of this is really the derivative of the first one, of one function plus another function, right? And so we can break it up as into those 2 pieces. The derivative of the first one plus the derivative of the second one. So that rule allows us to do that. And that rule has to be proved, but we can prove it by using the definition of what a derivative means. So if we use that here, then we're saying that the derivative of this together is the derivative of the first piece plus the second piece. So that's this plus this. And of course we know this is 3x squared, and we know this is 5x to the fourth, so that would be the final answer. Okay, so that would be using that rule. And if it's minus, then this is minus. If this is minus, then this is minus. Okay? All right, now number 4 actually comes next. So if you have a constant times a function, we have a rule that says we can pull that k outside of the derivative process. So, the reason is that would make the derivative easier to do, presumably, if you could take out part of it. You don't have to do the derivative of such a big thing. So, it doesn't mean you have to do this, but this is an option that you can do this. Okay, so for example, here, we have 10 times that, and this rule says that we can take the 10 outside, and that would make the derivative problem easier. We'd only have to take the derivative of x cubed, but you know how to do that already. So that would be 10 times 3x squared. So that would be 30 times x squared. Okay, so that's another rule. This number 4, which should be number 2. Okay, so it just says you can take the constant outside. Okay, so we want these rules because we want to be able to calculate lots of different derivatives, because we want to be able to work with lots of different functions, because in economics and physics and wherever you get lots of different functions, you want to be able to analyze as many of them as you can. Okay, so that's number 2 really, or whatever. Okay, and here's another one. Okay, this one we haven't done yet. This one is, we did plus, we did minus, so it stands to reason that we might look for a rule for multiplication of functions. Okay, we did addition of 2 functions, we did subtraction of 2 functions. How about multiplication? So the derivative of the product of 2 functions. So, for example, suppose you wanted to do this one. Okay, this is the product of x cubed and e to the x. Okay, so this rule will give us a way to do this kind of problem. Okay, so what does the rule say? So now I switched from one notation to the other. So I switched from using this notation to using the prime notation for derivative. Okay, so f prime times g, so you take the derivative of the first one times the non-derivative of the second one, and then plus the derivative of the second one times the non-derivative of the first one. Okay, so that's and again, we have to prove this, but you can read the proof online somewhere. This is called the product rule for derivatives. So I'm sure you can find that many places. Okay, and the answer is this, and an example, as we said, here we have one function times another, so this might be f, and this might be g. So we have the derivative of an f times a g, and the rule says you take the derivative of the first one, of f, and then multiply just the non-derivative of g, of the second one. Okay, and then you take the derivative of the second one and multiply it times the non-derivative of the first one. Okay, and this, now obviously we could switch these, right? And we'd still be asking for the same function, right? We're allowed to switch, right? So this should be symmetrical with respect to what we call f and what we call g, right? And it is, right? Okay? Now, it's not true, like this one was really simple, right? The derivative of f plus g was the derivative of the first one plus the derivative of the second one. But this is not true. The derivative of f times g, it would be nice if what? That was just f prime times g prime, right? That would be the nice simple answer, but it is not true. Okay, the answer is this rule here. Okay, so it looks kind of complicated, but you you can look at the proof of it, you can see that it's actually this way. Okay? So if we wanted to do this problem here, we'd said that it's the derivative of the first one, so that's what I wrote here, times the non-derivative of the second one, so that's what I wrote here, plus the derivative of the second one, which is what I wrote here, times the non-derivative of the first one, which is what I wrote there. Okay, so of course we can finish that by saying that this is what? What's this one?
3x squared.
Yeah, derivative of x cubed is what?
3x squared.
What is the derivative of x cubed? 3x squared, right? So this is 3x squared times e to the x. Okay? And then we have to do the second piece. So we have to put a plus sign. And then we'd say, what's the derivative of e to the x? And remember, that was the easiest derivative there is, because it's just e to the x. Okay, it's a little bit weird, but it's just e to the x itself, and then times x cubed. So that would be the answer. Okay, 3x squared e to the x plus e to the x cubed. Of course, you could simplify that a little bit. How could we simplify it? We could factor out the e to the x, right? So we could write that what? This can be written as e to the x times what? 3x squared plus x cubed. Okay, but this is still correct, right? Just, right? Okay, any questions about that? Okay, and then finally, so we did 1, 2, and 4. Okay, let's do another example of the product rule, just because that's new. So let's do another example. So suppose we wanted to know the derivative of x to the fifth plus 7x times x cubed plus 5. Suppose we wanted that derivative. Now there's a kind of another way to do that. Besides we could say that this is f, and this is g, and that's what we're doing now, calling it the product of these two functions. But there's another way you could do it, besides that, besides using the product rule, is what? You could just multiply this out first, and then you're just going to have a polynomial. Right? You're just going to have a polynomial, just a regular. Right? And then you can do the derivative of that polynomial piece by piece and get the answer, right? So that we could use that as a check to see if this product rule actually makes sense. Because we know that we can do it one way. So the product rule is kind of this strange way, so we can check whether the product rule actually seems to give the right answer. So actually, let's do it the kind of non-product rule way first. So what are we checking? X to the fifth, x to the eighth, right? And 7x, and 5x to the fifth. And 7x to the fourth. And 35x, right? Okay, so we can do the derivative of that, right? All right, let's not do it yet. Let's just try it the other way, and then we'll check to see. We'll finish this afterwards. So if we use the product rule, which is, where is it? Here. So I'll erase this one. So if we use the product rule on this, then here's F, and here's G. So the product rule says what? Take the derivative of the first one, the derivative of the F1, just times the non-derivative of the G1, plus the derivative of the G1 times the non-derivative of the F1, right? Okay, so let's do that. So I want the derivative of F. What is the derivative of F? What's the derivative of f? 5x to the 4th plus 7, right? Times what? G, the non-derivative of g, x cubed plus 5. Right, so now we just did this part, right? Now we have to do this part. So plus what? The derivative of the second one, which is here, so what's that? 3x squared times the non-derivative of the first one, right? X to the 5th plus 7x. Okay, so this is supposed to be the answer. Now we can check it by checking this one also. Let's first multiply this out. So what do we get? Okay, what do we get? 5x to the 7th plus 7x, plus 25x to the 4th plus 7x cubed plus 35, right? That's the first term here, this first piece here, right? Plus what? 3x to the 7th plus 21x cubed, right? Okay? Okay, so that's now, okay, we want to simplify that. What do we get? We have 8x to the 7, right? All right, 8x to the 7, and we have, what, 25x to the 4th, and we have 28x cubed plus 35, is that right? Did I do that right? 8x to the 7th, yeah, 25x to the 4th, 28, no that doesn't look right, is that right? Yeah, 28x cubed plus 35. Okay, now how about up here? What do we got? 8x to the 7th plus 25x to the 4th plus 28x to the 3rd plus 35. We get the same thing, right? Okay, so it seems to work. Okay, so, but you can't always, multiply it out like that. We did the first example we had e to the x times something else, times x to the 5th plus 26x or something like that. You can't do anything with that. So you have to use the product rule for that one. Okay? But sometimes you can do it a different way. All right, any questions about this? Okay, so that's called the product rule, and there's also a quotient rule, which is like a kind of complicated looking thing. You can look it up. Okay? I'm not going to go through it, but it's just another rule. What you do when you have f over g. Okay, the answer is, it turns out, it looks like this. F prime g minus g prime f. So that looks a little bit like the product rule, and then divided by g squared. Okay, so this is another rule. You just take the derivative of the first one times the non-derivative of the second one, minus the derivative of the first one times the non-derivative of the first one, or whatever I said, and then the square of the, not the first one, but the bottom one. Right, this is the bottom one, the bottom one. Okay? So that's just another rule, so let's not spend too much time on that, but you should maybe look it up so that when your economics teacher uses it, you won't be completely stumped by it. Okay? Any questions about that? Okay, so we did 1, 2, 1, 2, and 4. And we need one more. So we did the plus, minus, times, and actually I made reference to division. So you might think, okay, that's all, right? There are no other operations, right? And if you're talking about addition, arithmetic, these are the only operations. Plus, minus, times, and division. But when we have functions, we have another operation. So, I can talk about 2 plus 3, but I can also talk about x cubed plus x to the 8. So this is adding to functions, this is adding to numbers. So, there's an analogy between adding numbers and adding functions.